Hello, everyone. It's our great pleasure to meet with you today. We are truly excited about our collaboration and between the Saudi Space Agency and CASA, the Korean Aerospace Administration, in the field of capacity building, enhancing the knowledge and skill development. This collaboration includes inviting the leaders of space experts and professionals to discuss the key topics related to space, providing participants with the opportunity to ask questions and engage directly with the expert speakers. So it's also our pleasure to invite Chol Chord, the Director of Space Culture and Human Resources Development, to start with opening remarks on behalf of CASA team. Go ahead, please.
Yeah, thank you. Yeah, good afternoon, distinguished colleague in SSA, the CASA student, and esteemed guest from the Saudi Space Agency and beyond. It is my great honor to welcome you all to the 2025 SSA CASA Space Awareness Workshop. My name is Choi, in charge of the Aerospace, HR, and Culture Development Division. As the Director of the Culture and Talent Development at the Korean Aerospace Administration, I am delighted to be part of this meaningful exchange between our two nations. This year marks the first anniversary of Korean Aerospace Administration. In just 1 year, we have launched bold initiatives in satellite technology, deep space research, and importantly, talent development. Today's webinar reflected our shared commitment to nurturing the next generation of the space leaders. Since the signing of our MOU in March, Korea and Saudi Arabia have built a strong foundation for collaboration, from space research to startup support and joint education programs. This workshop is a powerful step toward realizing those goals. I believe that through the open dialogue, a shared knowledge, and the mutual respect, we can expand opportunities not just for our agencies, but for our youth and the global space community. Thank you again for joining us today. I look forward to the inspiring discussion and future partnership that will grow from the event. Thank you a lot. Thank you.
Thank you, Ms. Hanan, and thank you, Dr. Sheng Chol, for the introduction. To move on to our today's agenda, we'd like to invite Dr. Mariam Firdaus, Saudi Astronaut General Supervisor of University Affairs and Saudi Space Agency, to talk about human psychology and medical challenges in deep space missions. Welcome, Dr. Mariam. You can start. Thank you.
Thank you, Msha'il. Thank you, Hanan, and thank you, Dr. Sean, for your greetings. It's really my pleasure to be with you today. As a brief about myself, my name is Mariam Firdaus. I'm a physician, epidemiologist, as well I'm an astronaut in the Saudi Space Program. And today we're going to talk about the medical challenges in the deep space missions. So my outline is going to be more about space medicine, then what makes space dangerous. Later, we're going to talk about the medical risk evacuation from space, and we'll talk also about the medical event in missions, as well the medical system for deep space exploration. Then example for a previous medical system and the current medical system. And finally, I'm going to talk about the future of the space medicine. So first of all, as a background about myself, before I start this being an astronaut, I was a physician in the hospital, but I had a lot of passion about the public health. So I start to take many courses in ocean medicine, in aerospace, in different type of public health courses. So today I would like to start with you by what is the space medicine. So the space medicine, it's not a clinical. You cannot just treating cold or a flu. It's more about mission critical. You have to maintain the performance for the crew. You have to maintain the performance of the and the health for the entire crew. As well, it will cover the diagnostic the diagnostic procedures and also the emergency surgery in case if you got emergency cases or emergency cases. Of course, because the difference between the space in medicine and the space on Earth, there is no evacuation. The duration for the evacuation, it's between here in Earth between 5 minutes to 1 hour. But when we talk about the space, we are talking about more than 4 hours. So for this reason, space medicine, it's really a big thing when we are talking about a mission. Then what makes the space dangerous? There is a 4 main reason about the space, how space is dangerous. So first one, it's the environmental hazard. We have, like, for example, we have the radiation, we have the temperatures, because we are talking about the very cold temperatures, and we are talking about the very hot when we are exposed to the to the sun. As well, we having another atmospheric contaminate, as well the space debris, and eventually or lastly in this category, which is the decompression or the vacuum exposure. The second main reason, which is the psychological stress. When we are talking about the psychological stress, we are talking about the cardiac event. It's not happened till now, but there is let's say a small rate or proportion to have a cardiac event. Also, we having a visual impairment, as well the infection and the dental issue with the urological issue. The third reason for why space is dangerous is the mental and the cognitive health hazard, like the psychological stress. Here on Earth, if you having any problem, or you can take like a day off, but in space it's cost a lot. As well, we having as a second example is the fatigue, and the third reason it's the cognitive reason, and finally the psychiatric, like for example the depression or the isolation feeling in the in space. Lately, or the last category for why space is dangerous is the operational and the emergency hazard, like trauma and burn, laceration in the eye, and all of us we know that. For example, the famous astronaut Chris Hansfeld, he had an eye injury during one of the of his spacewalk during his mission. The last things is the inability to perform the critical task, maybe because you are tired, you are fatigued, you having any kind of operational reason. So this is why space is dangerous. And in this chart, it's like the medical event and symptom that occurred for NASA astronaut during the ISS mission through 40 expedition in the outer space. And we can see like the orthopedic reason, like the trauma, if you having a broken leg or broken arm, or maybe you having something with the shoulder, it's caused the main symptom or the main reason. As well, we having the skin symptoms, like the rashing and maybe some infections, some skin infection that may occur during due to many reasons in space. As well, we having the headache. The headache is the third top reason for having a medical event or a symptom in space. And why we having a headache? It's maybe it's mainly due to the fluid shift from the lower part to the upper part, and this causing a compression to the astronaut brain. As well, we're having many other causes, but this is mainly the three main causes for the medical symptom or a medical event in space. And now we are talking about the real things. This is two main events happened during the space exploration or during the mission, like cardiac arrhythmia, which shortening the mission from 11 months to 6 months, and that happened in May in 1987. And there is a case of sepsis that happened, and this shortening the mission from 26 days to 56, and it was in Salute in 1987, in 1985. And lastly, the suspected toxic exposures was shortening the mission from 55 days to 49 days, and this occurred in Salute 5 in 1986. And the other main event that happened and bended, but finally they aborted they didn't do they aborted the evacuation in case of toxic inhalation, suspected appendicitis, as well the urinary tract infection or a kidney infection that may cause a sepsis. So when we talk about deep space, we are talking about, I call it different games, because in ISS there is a real-time support. You're gonna be within 2 to 4 hours on Earth, but in case of you are in the moon or Mars or beyond, this is not the case. You have a frequent resupplying for the emergency, for technology, and there is an easy evacuation. But when we are talking about Mars, we are talking about no evacuation system, no life support system, and the resupply it's like limited, and the mission period it's between 2 to 3 years. So when we are talking about the medical our space medicine, we are talking about it's not an option in this missions. It's a mission backbone for the mission. Then when we are talking about the medical system for deep space, we're talking about, because there is no evacuation, so our policy or our let's say our system, it's built on three main things. First of all, the crew medical officer training, as well the AI driven clinical decision support, and the medical the smart medical kit. So let's take it one by one. For the crew medical officers, we are this officer should handle the trauma. He should handle the wound care, the dental procedure, any urinary catheterizations, as well the CPR in the microgravity, IV injection, and the fluid, and lastly the surgical assistant, which is this is the basic or fundamental things for any crew medical officer. So for this reason, during our training, we got a medical training. As well, I'm a doctor, but they trained me because as I mentioned before, the space the medicine in space is totally different than the medicine here on Earth. Second things, it's the AI decision, clinical decisions, because the crew might have no doctor, so we rely on the AI for their guidance for diagnosis and treatment. And for example, onboard system trained to recognize symptom via sensor, via images, and via report from the other crew, and this is our recommended next step. And finally, for the medical kit, it should be portable, compact, and let's say a long shelf life. We don't have an expiry for in space, so it must cover the emergency medicine, and it should be also including the monitoring for ultrasound, for ECG, and for other vitals. Also the emergency surgery, as well the resuscitation system like an oxygen and ventilator and defib machine. So this is an example for a previous medical system, like in the right side of the in the slide, you can see the Mercury medical kit. It was like when we go to hiking anywhere, it's more about a first aid. But later, when they start the Gemini and Apollo, you can see like they insert more medical mission devices and medicine. And for the current medical system, like in the shuttle, you can see in the right how they are like categorize the things. But in the International Space Station, it's more about having a system, like a system for everything. And I remember our training during my training for the emergency event. It really wasn't like easy for me. I used to have a CPR event in my training, but to be honest, at that training, it was really hard because you have to find a position for yourself to helping your crew or your friend during that event. So this is an example for the current medical system. So now about the future of space medicine. What is the future of space medicine? As we said, it should be AI driven, it should be autonomous and integrated, because we are not building a first aid kit, we are building smart, zero fall hospital in a box. So to that, I finish my presentation. I'm open if you have any questions from the audience.
Thank you, Dr. Mariam. It's very impressive to see how our bodies react during space missions. I would like to invite anyone who has any questions to Dr. Mariam. Please raise your hands and we shall take it in order. Thank you.
아무도 질문 안 하니까. Hi.
Hi,
Can you
Dr.
hear
Jay.
me?
Yes, loud and clear.
Okay. So just I'm curious, in Saudi Arabia, how do you kind of cultivate or train the astronaut? So do you have like astronaut training center?
Thank you, Dr. Jay, for these questions. To be honest, yes, we don't have any astronaut training center as a center, but we have a program. So we are building our own programs with the collaboration with the other agency and with the other local entities. So we are aiming to localize this kind of training. So, for example, last year we had multiple programs, for example, for the cell culture, because we are focusing more on doing research in space. So we are not, all of us, we are not Rihanna. I mean, for my case and Ali, this is their first time to deal about to deal up more on cell, on having a cultures and dealing with the agars and microscope and all of these stuff. So we start to having this with the local entity as well. We are leverage our connection with the other international agencies.
Thank you. I think recently the smart healthcare system, so tiny sensors that can be integrated into like any smart devices, those things are really being developed, and I think it's more powerful. And later on, I think the use of these smart health monitoring devices seems to be very essential. Particularly, it'll be helpful in space. So, do you have any opinion on that?
To be honest, you came to the right person, because since, like, for example, I'm caring more about the sleep and the sleep quality. So since 2017, I'm monitoring my sleep through this AI smart devices. And when we start our training, this was essential for us. I mean, during the selection and even later after we got during our training. So they usually they hooked us with the devices that monitoring our respiration rate, our heart rate, our sleep quality. So I'm really big fan of that. It's not only for space; it's even for the normal for people, especially people with the chronic diseases, like for example the elderly people. And we use this kind of devices here in Saudi very frequently. And if you know that before like 2-3 weeks we have the big season for us, like the Hajj. So our Ministry of Health, it's promoting the AI and promoting this kind of devices. And you can see you can say that it's become like a country trend to monitoring this kind of symptom, or using this device like widely.
Okay, thank you very much.
Thank you, Dr. Ray.
Any more questions, ladies and gentlemen? Okay, I think we can proceed to our next topic in the agenda. So I would like to welcome Dr. Val Monsami, Deputy CEO at Saudi Space Agency. Dr. Val will take us through space weather. Thank you, Dr. Val.
Okay, thank you, Michelle. Just let me share my screen first. Okay. Just one important note before I start. First of all, thank you for this joint collaboration between our institutions. We truly appreciate it. There is right now a launch that's happening on the X4 mission, and there's 4 astronauts that are going up on the International Space Station. And just out of interest, the Saudi Space Agency ran a mega challenge across the MENA region, soliciting experiments, and there were 80,000 entrants, 80,000 entrants. I think we shortlisted 18,000, and we have 10 experiments that's going up on this particular mission, including planting seeds, and there's some experiments on testing gyroscopes on the International Space Station. So that's going up in the next few minutes, or should be launched right now. As Dr. Mariam indicated, there's a mega impacts on the human body physiologically, and there's 2 primary components. The one is on the microgravity environment, and the second is what we would refer to as space weather, because that has an impact in terms of radiation or radiation exposure in space. So this particular presentation is just going to give you a sense of what space weather is and why it's such a big topical issue when it comes to space exploration. So what is space weather? There's two areas that we kind of look at. The one is on the sun side, and then the other one is on the earth side. So on the sun side, we understand, when you look at any star, we're seeing two hydrogen atoms being fused and they create helium. And there's a lot of energy that's being released at any point in time. And so we're seeing around 386 billion megawatts released every second. And so the energy that's coming out is in terms of energy, particles, and there's also, the sun is also magnetized. So it has a magnetic field. And those particles, the electrons and protons that are coming out of the sun, we refer to as plasma. But the sun itself is not a solid body. It's actually gaseous in terms of the plasma. And so the rotation of the sun is not fixed or not solid. So the equator would rotate much faster than the polar regions. Different activity cycles. We see 27-day solar rotation, essentially, near the equator. There's 100-day active region developments that's sort of happening on the sun. But the most important one for us is what we call the 11-year cycle. We also see a 22-year cycle and an 88-year cycle on the solar activity. So essentially what's happening, you have a lot of energy or plasma, which is high energy electrons and protons coming towards the Earth. So on a very quiet day, when the sun is quiet, the plasma that's coming out from the sun is around 400 kilometers per second. That's the average velocity of the plasma. So we're continuously being bombarded by this plasma. But there are times when the sun gets very active and that velocity can go up right up to 1,000, 1,200 kilometers in some instances for the very severe storms. So that's the velocity of the plasma that we see. So we're seeing this constant solar pressure given that's being spewed out from the sun in terms of the plasma. But if you look at the Earth's magnetic field, so at the core of the Earth's magnetic field, you have a molten kind of a lava that's flowing that's also has charged particles in it. And if you know from school, if you have a current that's rotating, you create a magnetic field, essentially, the right-hand rule. And so you have this dipolar magnetic field. And what's actually happening is the solar plasma is squashing the magnetic field on the day side. And some of that plasma goes over onto the night side. And it grabs the magnetic field on the night side into a long tail. And we call this a magnetotail, and the whole structure is called a magnetosphere. And this is essentially the solar plasma interacting with the Earth's magnetic field. And then as you get lower down into the Earth's atmosphere, we have what is called the ionosphere, around about 100 to 300 kilometers. And there we see a lot of these electrons that are coming from space that's kind of embodied into what we call the ionosphere. And this also is affected by extreme solar activity, and we'll see that in a few slides from now. So effectively, what we're paying attention to is the sun and what's happening on the sun and how it impacts and influences the Earth's magnetic field and how it moves charged particles around in the magnetosphere. So as I indicated, the sun goes through an 11-year cycle. It goes from solar maximum to solar minimum. So it gets very active and then it starts to quieten down and then it gets very active. And this happens over an 11-year cycle. So right now we're just going past the solar maximum. So we achieved the solar maximum kind of earlier this year and we're starting to just go through the declining phase. So the sun is still very active. And what's interesting, if you look, we track what is called the sunspot numbers, the number of sunspots we can see. So effectively, if you take a magnifying glass and if you reflect the sun on a piece of paper, you see these dark little dots, and those are the sunspots. And if you count the sunspots over the 11-year cycle, they will follow this peak that we're seeing in the middle. Now, what's also interesting, you'll see just before the 1700s, you'll see that the activities, there's no activities. It kind of went very quiet. That's called a Maunder minimum. And there's some very interesting impacts around what happened during that time. So if you cut a tree, for example, you'll see these ring structures in the tree. During that time, all of the ring structures disappeared. So there's a linkage between life on Earth and what's happening in the sun, direct linkage. What we also found out during that time, that the pigeons and animals that use navigation, like the whales in the ocean, they were all flying and swimming haphazardly. It seems like they have built-in magnetometers that uses the Earth's magnetic field and somehow linked to the sun, which we quite don't understand yet, but everything is linked back to the sun in terms of organic life. So when we look at the sun in terms of what are the types of activities coming out, the one is what is called a solar flare. So there's a massive blast of plasma that's coming because of some very disturbances that's sort of happening more on the surface of the sun, and that plasma is being released very violently, and that energy that's captured in that plasma is around 40 billion atomic bombs. So it's a massive explosion essentially. We also have what is called prominences, and these are like just a minor burst of gas just on the surface of the sun, and that doesn't actually influence the Earth itself. So it's very localized. Another localized event is called coronal loops. So as I indicated, the Earth, the sun has a magnetic field, and what we see sometimes is the magnetic loop structure, and the gas is sort of trapped on that particular structure. And so the last one is the coronal mass ejections, where you have a massive ejection of coronal mass. And so the two events that we particularly pay attention to is the solar flares and the coronal mass ejection, because that actually reaches the surface of the Earth. So as I indicated, the physics behind the magnetosphere is very complicated. There's a lot of current systems that are kind of flowing around. And what we see is the compression of the day side, stretching of the tail on the night side. And we also have the formation of what we call the radiation belts. And in fact, the very first scientific experiment was to sense the radiation belt, and that was by Van Allen. And we refer to some of the radiation belts as the Van Allen radiation belts. And so we see induced currents that are happening, and I'll talk about that just now in a few slides. So what is the impact of the space weather? So we have all of the plasma that's being spewed out from the sun during very active activities, and that reaches the Earth, and it has an impact on the Earth's magnetosphere, the magnetic field. And by the way, I should mention, if the Earth did not have a magnetic field, you and I would not exist on this Earth. It actually helps to protect against the radiation from the sun. Without it, life wouldn't exist on Earth. So the impact of this particular space weather, when you have this plasma that's being spewed into space and it's reaching the Earth, some of that energy gets into the magnetosphere, and those charged particles are now floating in outer space, and they actually get down to the Earth's ionosphere. That means you have more charged particles in this particular environment. And if you've ever been to a doctor and you took an X-ray, that's high energy particles that are actually bombarding, and they actually go through your skin, but not through the bone structure. So these charged particles are very similar in nature. In fact, there's X-rays as well that's coming from the sun. That's one of the experiments we'll be conducting next year. So what does this do? It's very dangerous for astronauts, because these charged particles, if they hit your skin, they kill the cells, and it also causes cancer. So astronauts are prone to cancer as well because of the excessive radiation. And some of this radiation can actually damage satellites because they charge particles, and the satellites has many electronics. And if the charged particles interact with the electronic circuits, they actually destroy the circuits as well. And then what you see on the ionosphere, because we're pushing in electrons into the ionosphere, you create these current systems. Now, if you understand Lenz's law from high school, if you have a current that's flowing in a particular wire, and if you have a wire parallel to it, and if you change the current system, you'll see a current induced in the second wire. So if you have a current system in the ionosphere and it's changing, you will see, if you have, for example, an electrical wire, electrical grid, or even an oil pipeline, it'll actually, the current system in the ionosphere will induce a current on the electric pipelines and the electrical grids as well. And it also has an impact on the signals coming from the satellites, which I will talk about just now. So it has multiple impacts on technologies here on Earth and the ground, technologies in space, and also on human health as well. So what we're seeing is a disruption to radio communications is one of the big issues. So, for example, if you're flying, when you have a flight, the pilot is communicating to a ground station, and the way the pilot, he or her, does that is when they talk through the communication system, this signal is bounced off the ionosphere, and then it reaches the ground station or the ground segment. Now, what happens when you have too much of electrons? That signal gets absorbed by the electrons. So the pilot is unable to communicate with the ground segment. The other impact, if you're flying as well, because you have more radiation, that means as a passenger, you'll get exposed to more radiation. And so that could cause radiation damage on your skin and so on. As I indicated, the big issue there is around cancer and so on. And then impact on the electrical power grids, the pipelines, and then disruption to radio navigation signals. So most of us are using GPS as an example. And what actually happens is when this ionosphere, when you put more electrons into it, the signal that's coming from the GPS or GNSS satellites, when they come through the ionosphere, they get deflected. And that means there's a deflection in the position and creates an error. So if you're driving and using your GPS, you'll find that you're actually on the side of the road. And some applications require very accurate navigation signals. And so that can actually have an impact on the error signals and navigation. So how do we measure the effects is on the spacecraft, but we also use the spacecraft to measure. So what you see on the extreme left is what is called a sonograph. So it's a satellite that's sitting in the L1 libration point. So the L1 libration point is a point between the Earth and the Sun, where the Sun is pulling at that point and the Earth is also pulling at that point. But the forces are balanced. So it's a zero force on that point. And we put a satellite and it just orbits around that particular point. And what this satellite is doing is it's looking at the Sun, but blocking out the core of the Sun and just looking at what's coming out of the Sun. And so what we're seeing here is a solar coronal mass ejection that's coming towards the Sun. And you can see it's saturating the instruments because there's a lot of charged particles that are coming through. So we're using this as an observation platform to see what's coming towards the Earth. So it gives us an early advance warning. As I indicated, if you have a current system in the ionosphere, you generate a current system in the electrical grids. And what we do find sometimes, because remember, if you have a transformer, you take a current and you're stepping it up. But when you step it up, you're amplifying the current. And if you have additional currents that's coming from space that's induced into this electrical grid, it actually blows up the transformers. And we've seen this happen in, for example, in Canada, in Quebec, in 1989. There was a massive energy shutdown. The entire electrical grid just shut off, purely because of this induced currents on the electrical grid. And then we have some ways of actually categorizing. So NOAA, as an example, together with the international community, they look at these events and they have a category in terms of ranking what we call the geomagnetic storms, okay? And they will classify these storms according to this ranking. Another metric is how much of radiation is coming into the Earth's environment. So they have another classification to tell you whether this storm is going to be very high radiation dosage or low radiation dosage. And then we also have another classification called radio blackout. So it can also tell you whether you're going to lose communications on that particular day because of this particular solar activity. So the use cases that we're currently looking at is quite a few use cases. As I said, communications blackout, radiation exposure, impact on the astronauts, electrical grids, oil pipelines. And by the way, the mining industry normally conducts surveys. So they fly an aircraft, and that aircraft is sensing what's on the ground. And those instruments are actually impacted by these storms. The other big issue, especially when you're talking about artificial intelligence and the Internet of Things, where you have sensors in the ground, and then you're pulling off information from those sensors. Those sensors are actually affected by space weather, where it could actually induce currents in those particular sensors as well. So the biggest interest on space weather is also an insurance issue as well, because a lot of the satellites that we actually launch are insured. So Lloyd's of London, as an example, one of the insurance companies, is very interested to understand what is the risk. So they pay particular attention to what's happening with regards to space weather, so they can assess the damage and how much they pay out and so on. And then we monitor space weather in two different ways, either from the ground or from space itself. From the ground, we have what is called an ionoson. So this is essentially an instrument. So it's a tall mast. It sends a signal into the ionosphere and it looks at the reflection. And that tells you how much of electrons. And that also gives us a sense of how the ionosphere is being influenced by what's happening on the sun in terms of space weather prediction. And it also gives us information of how those radio waves from GNSS satellite to communication satellite is actually passing through the ionosphere, so we can understand more how to mitigate against some of the error signals. The other way of measuring the impact on the ground is what we call magnetic stations. So if you have a magnetic compass, if you have a current system close to the magnetic compass, it will deflect the compass either up or down in the azimuth or even sideways. And we use that as a measurement to get a global sense of what the current system looks like. And in fact, near the equatorial region of in the magnetosphere, there's a whole current system called the disturbance storm time index. And that tells you how much of current is actually in the magnetosphere. And if that intensifies, for example, the astronauts are not allowed to do EVAs or extra vehicle activities. That means going outside the space station, as an example, because they will get radiated when that happens. So we use the magnetometers to tell us what the current systems looks like. And there's a whole network of these magnetometers all across the world, as you can see on the top left-hand side. And then we also have a solar observatories where we have a large telescope that's purely focused on the sun, and it gives you a lot of granular detail in terms of what's actually happening on the surface of the sun. And that is actually used to predict what's going to happen, whether there's solar activities coming towards the Earth. And then we also have a GNSS scintillation receivers. So for example, if you have a GPS receiver, and if you know the exact location, and if you're taking a GPS reading, and it'll tell you you're actually in this location as opposed to this. So that means there's an error signal. And that error signal means that there is more electrons in the ionosphere. So we can use that to measure how much of electrons in the ionosphere as well. So this is also a function of what's happening on the sun itself. And then on the space-based instrumentation, I gave you an example of satellites sitting in the L1 libration point, and there's quite a few of them. SOHO was one of them. And we also have satellites in the geostationary orbit that's also giving us some information what's happening in that area of the orbit as well. So there's a number of satellite missions we used to predict what's happening and to sense and observe what's happening in the Earth's magnetosphere. Interesting enough, we had the Saudi Space Agency has developed a satellite which will be flown in the Artemis 2 mission. So the Artemis 2 is a NASA mission where they're flying the 4 astronauts that are going to go around the moon and come back. And we have a satellite that will be ejected around 70,000 kilometers. And that satellite will then come back towards the Earth around 500 kilometers. And so it's a highly elliptical orbit. And this satellite has radiation sensors that will give us a sense of how much of radiation is there, how much of X-rays is in that environment, how much of what the magnetic field looks like at that particular location. So we will be collecting these data points and seeing how that matches up if there's a solar event happening as well. And so if you look here, this is what the magnetosphere looks like. And then the little red ring is essentially the orbit that the satellite is going to be flying into. So that's a mission that's going up in the first quarter of next year. And this is a space weather satellite. So this is something that we started setting up, including a space weather center here in the Saudi Space Agency. So thank you for your attention, and I'll hand over back to you, Michelle. Miriam has a question on, Dr. Miriam has a question on the chat box. What are the differences between solar minimum and solar maximum? So thank you for the question. So essentially what I showed was a number of different events that come from the sun. You have the solar flares, coronal mass ejections, the prominences, and so on. So during solar maximum, you see a lot of this. During solar minimum, they virtually disappear. So during solar maximum, you need to pay attention because that means there's a lot of charged particles are being put into the magnetosphere, and then it gets very quiet during solar minimum. And that's probably the best to do space exploration mission times. Good. There's a question from Kichan. Yes.
Thank you for your wonderful presentation and explain the key space weather phenomena in such detail. So I have a couple of questions, but the first one is that in the last high-level meeting between the SSA and CASA, I understand that SSA suggests some cooperation with Korea in the space weather field. Because the meeting time was very short, so we couldn't go into detail. So I'd like to ask, are there any specific project or plans for the space weather cooperation with Korea? So if so, we'd really appreciate if you could share that.
Yes.
Yeah.
Okay.
Yeah.
Sure. Carry on.
Yeah. Another question is that the CASA has the dedicated Space Weather Operation Center. The name, the Korea Space Weather Center, is also CASA's umbrella. So is there any dedicated center for space weather forecasting or operation in SSA? That is my last question.
No, thank you, Kichan, for those questions. Definitely, because space weather is something, because the Saudi Space Agency is fairly new, and space weather is something that we're trying to bring into focus as one of the key areas that we should be doing some research. And so we have, for example, right now, there's a group of our engineers are in the UK being trained up on the space weather satellite, but some of our scientists are also involved in terms of looking at the payloads as an example. And then we're also definitely looking in terms of setting up our own space weather center. And what we are looking for is training forecasters, how to forecast some of the solar activities, because even during that particular satellite mission, we need to understand what's happening in the magnetosphere, where is the satellite in the magnetosphere, what are we expecting to, so it goes into the concept of operations of the satellite itself. So understanding the physics and how to interpret those particular measurements is something we're still looking and developing within the agency. So I would be certainly open to that discussion in terms of collaboration. Thank you for that, yes. Dr. Jahan, you had a question as well?
I think, Dr. Val, we have a question in the chat.
Oh.
Okay, can I ask one thing?
Yes.
So anyway, it's very interesting to learn that the CubeSat is contributing to kind of space weather prediction. So I want to learn more about the CubeSat mission. What's the orbit and what kind of payload is, you know, is used for that CubeSat? So can you explain that, please?
Yeah, so the CubeSat will be in a highly elliptical orbit, so it'll be 70,000 kilometers and then 500 kilometers. So it's, and by the way, that particular orbit is very difficult to get to. And I think because of the lunar mission, we are able to piggyback on that particular mission. It's a very expensive mission to put a satellite in. So we're quite thankful that NASA opened up that collaboration. I think there's 5 countries that have satellites on, which will be on the back end of the Orion, where the astronauts are sitting on the back. You will have all these 5 satellites that will be deployed as they get closer, they move towards the moon. In terms of, so we had a, sorry, was there follow-up? Okay. In terms of the payloads, we had our science community. Sorry, there's a bit of an echo in the back end. In terms of the mission itself, we had our scientific community giving us ideas. So we have some research being done on heliospheric physics, and there has been some research in the past being done on space physics. And we asked some of our professors in some of the universities to give us a concept for the mission. And then they came up with a number of ideas, and we had a selection team. And so we identified 3 particular payloads on this particular satellite. It's a radiation sensor that will be measuring the radiation in terms of the protons and the electrons. And then we have an X-ray detector because there's a lot of X-rays that will be injected into the Earth's magnetosphere. And then we're also taking up the measurements of the magnetic field at those particular observation points, because the magnetic structure changes in different regions. For example, if you're crossing the magnetopause, the boundary between the solar wind and the Earth side, there's a particular structure that we want to see. So the magnetic measurements, how the radiation changes between those 2 regions, and the X-ray flux as well, will be something that we've been monitoring across these various boundaries.
Okay, thank you.
Thank you. Yeah, the question is the Artemis 2, and wonder what the specific area that SSA has contributed to in the project. Yeah, so the payload assessments, we've done all of that. And by the way, we have what is called a concurrent design facility. And so we took that particular mission and we did a whole engineering design for that particular satellite. And then obviously we worked with some partners in terms of co-developing this particular satellite. And we're actually building the engineering model right here in the kingdom. So there's some labs that we've set up to actually build the satellite, but we're working with a partner on the flight model itself. We're also setting up some, as I said, the Space Weather Center, but we're setting up some ground instrumentation right now. We're looking at some GNSS receivers to help us measure the total electron content, so that by the time the mission is flying early next year, we would be doing ground-based measurements as well, and we can have multiple data points that help us to understand the science. So there's a lot of things that are being done in terms of planning for this mission, including a mission control, which we will be setting up here, right here in the agency as well. Back to you.
Thank you.
Michelle. Thank you.
Thank you, Dr. Val. So moving to our next item in the agenda, I would like to invite Dr. Daniel J., Vice Director of the Korean Advanced Institute of Science and Technology, to take us through the scientific mission design options for asteroid exploration. Floor is yours, Doctor.
Excuse me, Michelle? Hanan?
Yes.
Hi, so we have multiple sessions going on right now, and there's some trouble with timing. Would it be okay if we start at 10, so 8 minutes later?
Thank you for letting us know. If we can start with Dr. Jin Lee, if he's available now, so we can switch between the two.
Yeah, so we have multiple things going on right now, and
okay.
The person that's supposed to be speakers should have been done at this time, but we are still taking questions. So would it be okay if we start at 10 o'clock, 10:10?
Okay, so it's 7 minutes.
Right, 7 minutes of break, and then we can start.
Yeah. So since we have 7 minutes, I think if we can take some questions about previous sessions, just to use the time.
Okay, thank you for understanding.
If you have any further questions for the previous sessions we did, I would like to invite anyone and everyone to to raise their hands if you have any questions about space medicine or space weather, since we have more time for questions, luckily.
So, hi, since I'm caught in the trouble, I'll ask a question. So I had a question about the previous presenter about the heliophysics. We have a mission in CASA called the L4 probe mission, where we are sending a spacecraft to an inclined orbit about the sun. And one of the main purpose of the inclination about the sun is to look at the poles. So I wanted to ask, what kind of scientific advancements do we have by looking at the pole of the sun? Thank you.
Okay. Now, thank you for that question. By the way, I'm not a heliospheric physicist. I'm more a space physicist in terms of understanding the magnetosphere. So the one thing to understand about the sun, as I said, it's not a solid structure. It kind of rotates much quicker at the equator. So the rotation at the poles was slightly slower. So if you look at it from that perspective, there's obviously a lot of like twisting of the magnetic field and some of the gas. And so there's a lot of turbulence that's kind of created. And by the way, the sun also changes its magnetic field orientation every now and again. So the magnetic field will essentially flip over during the solar cycles, essentially. So it's alternating between north and south on the solar surface. So those are the kind of key aspects that we kind of looking at, and then also to see what sort of events would be coming out of the polar regions as opposed to the equatorial regions. Most of the events that we see is more equatorially based, but I think understanding the dynamics even at the polar regions is going to be very key. Just one thing I should mention. We are setting up a center of excellence for astronomy and space science here in the kingdom. And the very first center of excellence that we're looking at is on heliospheric physics. We do have some universities focusing on heliospheric physics and have solar telescopes as well. And so that will be very key, if maybe a possible area of collaboration, because it's an area that we want to build capacity in terms of understanding the sun and its impact on the magnetosphere. Thank you for the question. So maybe while we're waiting, I should maybe take advantage. One of the things that is very critical, ICAO is the International Civil Aviation Organization, and it has passed a regulation, I think it was in 2019, where it says that all flights, and we're talking about aircrafts, long duration flights, need to have space weather information as part of the flight plan. And the reason for that is there's three impacts on aviation during active space weather events. The one is, as I indicated, when the pilot is communicating with the ground segment, and if there's a lot of electrons thrown into the ionosphere, they lose the communication signal. So you have a communications blackout. So that's the first impact. The second, you have excessive radiation in the environment. So that implies there's radiation exposure to passengers. And then the third one is, in these days, we're using navigation signals to steer the aircraft, to figure out where we are and where we need to go. And some of those signals during these active events, they actually get absorbed in the ionosphere. So we lose the navigation signals as well. So ICAO is essentially now regulated that the flight plan needs to include predictions around space weather. And so there's a number of regional centers that have been set up. There's one, the US is. Thank you.
Thank you. Thank you. Seems that Dan is preparing for his presentation, so just to be a little more patient, please.
Dr. Val, I think we have another question in the chat about specific data for researchers to analyze.
Make his presentation soon, so you may answer the question by chatting.
I'll say it in the chat. I'll answer it in the chat, yes. Okay, thank you.
Okay.
Yeah, this one I think was. Yeah, but yes, check it this one through the. Oh, okay. Can we have a check on Teams? Did you hear us?
Anyone in
Yes.
Teams?
Hi. Yes, we can hear you.
Okay.
Yeah, okay, so I'm going to introduce the next speaker. Professor Daniel J. Shears. He's going to introduce about the scientific mission design option for asteroid exploration. So as you notice, so we have a 30-minute for the presentation and 5 minutes of question. So please start whenever you're ready.
Okay. Thank you very much, and thanks for the invitation to be here. I'm very honored to follow a good friend, Dr. Tsuda, and talk a little more broadly about asteroid missions, whereas he did a very deep dive into the Hayabusa 2 mission. And you'll see as I go through my presentation that the Hayabusa 2 mission actually achieved many of the most important goals that we have for these space missions. So before I go into more detail about what some of our design options are, I want to talk briefly about the motivations for why we are interested in studying asteroids. And in fact, these 4 motivations were the same motivations that Dr. Tsuda presented to us at the end of his talk, showing the significance of these. The first motivation is to understand the science and nature of these bodies. These small bodies, what we call asteroids and even comets, are remnants of the early solar system, and they give us a pristine record of the chemistry at the solar system's formation. They also, understanding their movement in the solar system over time, actually allows us to use them as tracer particles that tell us how the larger planets have actually migrated over the last few billion years. These small bodies have also shaped life on Earth by delivering water and minerals to the early Earth and by causing occasional impact extinction events. They're even a unique form of matter in and of themselves. As rubble pile asteroids in microgravity situations, when we study them, we actually can study the mechanical properties of bodies that have been present in the solar system from the earliest time. Another reason is exploration. These near-Earth asteroids are a natural destination for future human exploration and are, in general, the most easily accessible bodies outside the Earth-Moon system. And in fact, NASA has even very seriously considered these as targets for human exploration in the past, and they may be considered so in the future. Another important area is understanding what resources are available in space. And extracting resources from asteroids has been thought about for many, many decades. It really has been a science fiction dream. However, there are startup companies that are forming pretty much every year in order to push this dream closer and closer to reality. And some of these companies are now actually launching satellites to go visit asteroids sometimes without complete success. But I think very soon we'll start to see additional activity on this front, which is very exciting. Maybe the most important reason why we want to study asteroids is from a societal reason. We know that these asteroids are impacting the Earth all of the time. Anytime you see a shooting star, or when you see something larger like the Chelyabinsk meteor, these are asteroids intercepting with the Earth. We know that they've caused large-scale extinctions in the past. A rational question for us is, if we find an asteroid that's on a collision course with Earth, and we may have decades of preparation time if this should occur, could we actually stop it? And the answer, in fact, is we might be able to stop it. There have been missions that have been flown, most significantly the DART mission a few years ago by NASA, that have actually tested out techniques for pushing asteroids off collision courses. So with that background about why we're interested in asteroids, I think it's important to understand, how do we actually observe these bodies? How do we know that they're out there and what their properties are? And the most fundamental way that we do this is through Earth-based observation. And everything else flows from these Earth-based observations. So these are a prerequisite for all of our exploration activities of asteroids. And there are several main techniques that we use to characterize them, and I won't go into much detail, but I want to mention them. The first is astrometry, which is the discovery of these bodies by astronomers and the determination of their orbits, so we know where they are in the solar system. Another approach we use is photometry, which is measuring how the light reflected from these bodies varies over time. That tells us information about how fast they spin and what their shape is. We can also look at these spectrally, meaning that essentially we are looking at the colors of these asteroids, and that gives us insight into the mineralogy and what they're made out of. We can also look at them in the thermal wavelengths, and this gives us precise size estimates of these bodies and properties of the asteroid surfaces. And finally, what we often have used in the past and still use is radar observations of these bodies, which give us very precise orbits and determine the shapes and spin states of these bodies. And here's a sort of a collection of these different measurement techniques. Astrometry allows us to discover them and determine their orbits. Photometry allows us to see how they spin. Spectra tells us information about their colors. And then radar actually can give us shape models and orbits and spin states, as represented here. So with that being stated, this very fundamental approach to discovering these bodies, what we've done is progress from these ground-based observations to space-based observations. So now let's talk a little bit about how we can observe these asteroids using spacecraft from the space environment. And there are really 4 different ways of interacting with them that we should identify. The first and simplest is what we call flyby missions, where we have our spacecraft and it flies usually rapidly close to and by the asteroid. This can give us very important information about the body, and by far it's the easiest way of accessing the scientific information. But it's in some sense, it doesn't give you a full picture. It's like if you wanted to understand the city of Seoul, and if you just drove through the freeways, you could see a lot, take a lot of pictures, but it's very different than stopping and getting out of your car and investigating. So if we go into a rendezvous mission, we actually are stopping at that body and we are interacting with it, at least in the orbital sense, the orbital space. And it allows us much longer time periods to observe the body, measure properties of the body and the like. The next stage after that might be a sample return mission, such as Hayabusa 2 and OSIRIS-REx in Hayabusa, where we actually go grab a sample and then bring it all the way back to Earth. That's another level of difficulty for these exploration missions. And finally, I'm missing the tag here, but while we're rendezvoused with the body and beyond just capturing a small sample of the body, we can actually start to explore the surfaces of these bodies by putting vehicles, landed vehicles, on the surface to determine the mechanical properties of these bodies and how we can actually move material around on them, which would be a prerequisite for any resource utilization. So these are the four main areas. And what I'm going to do is sort of walk through a variety of asteroids that we've visited in the past, talking about what we've been able to achieve using these different exploration methodologies. So first off, if we represent here a picture of all of the asteroids that we've explored, and I believe I have pretty much most of them here to date. You see that there are many, many of these bodies. And instead of talking about each one in detail, we'll do some large-scale sorting of these bodies by how we've actually explored them. So the first one we'll talk about are these flyby missions that I spoke about, where we don't stop the spacecraft, but we go by and we take images of that body. So what can we achieve with the flyby exploration mission? Well, we can get resolved imaging of the body at multiple wavelengths. We can determine the shape, at least a partial shape. We fly by so fast generally that the body doesn't have time to turn while we view it. So we just see half of the body. Sometimes we can estimate the mass of the body if it's large enough, if we fly by slow enough and close enough. And we can also sometimes get estimates on the spin state of the body. So there are a whole host of past examples. And here I really have a number of firsts that have been done with different spacecraft, starting with the Giotto mission in the Halley Flotilla back in 1986. This was the first comet where we had a flyby. The Galileo mission to Jupiter, a NASA mission, actually flew by the first asteroids, Gaspra and Ida, and determined that what their shape looked like, and that this Ida asteroid was actually a binary asteroid. The NEAR mission, which I was a part of when I worked at JPL, flew by the asteroid Matilda. It was the first time we were able to estimate the mass of an asteroid from a flyby spacecraft. Then we could talk about the New Horizons mission, another NASA mission to Pluto and then Arrokoth. And these were the first flybys of Kuiper Belt objects. The DART mission, the NASA DART mission to Didymos, was really the first impactor in planetary defense tests, and in some sense was a flyby, although it only had half of that flyby. It came in, it never left. And there's many, many other flyby missions that have achieved great science, but they're not first, so I'm not mentioning them here. There are also some significant upcoming flyby missions. The Hayabusa 2 Shark mission, which Dr. Tsuda spoke about, has a flyby of the asteroid Torifuni next year. The Lucy mission, the NASA Discovery mission, is going to start its flybys of the Trojan asteroids starting in 2027, in a few years. There are also a few missions in development. The Emirates Main Belt Asteroid mission is a mission by the UAE. It has flybys of 6 main belt asteroids and it launches in 2028. And it rendezvous with the 7th, but I'll talk about that in a minute. And then also the Destiny Plus, the JAXA mission, that will be the first one to fly by an active asteroid in 2028. And here we just have some examples of the images that we can get from our flyby observation from a variety of different missions, including the Chinese mission over here on the right that flew by the asteroid Tutatis almost a decade ago or so. So if we have all the asteroids that we visited, these blue ones are the ones we just had a flyby. The next level is a rendezvous mission, which enables a high resolution imaging of the surface at centimeter in scale and smaller at multiple wavelengths. Gives us detailed shape and spin state, gives us a mass and a gravity field, surface and subsurface measurements that are possible. So we really amp up the level of science. Past examples are the NEAR mission, which was the first rendezvous mission to an asteroid, Eros. The Hayabusa mission was the first to rendezvous with a very small asteroid, Itokawa. The Dawn mission, which went to the Vesta and Ceres, the first dwarf planets. Rosetta mission, the first rendezvous with a comet. Hayabusa 2 mission, the first rendezvous with a C-type primitive asteroid that was closely followed by the OSIRIS-REx mission. Here, there are many upcoming missions that actually represent firsts. The Hera mission, which will be the first rendezvous with the binary asteroid. The OSIRIS-APEX mission, visiting the asteroid Apophis. First tumbling small NEO that will be visited, although it may be beat out by the Ramses mission. The Psyche mission will go to the first metallic asteroid. Hayabusa 2 Sharp will visit the smallest asteroid visited to date, 1998 KY26. And then the MMX mission, also from JAXA, will visit the asteroid Phobos, and that should launch next year. Again, in development is the Emirates Main Belt Asteroid mission from the UAE, which will rendezvous with the Main Belt Asteroid Justitia, that has a very unique asteroid spectra, and the planned Chinese Tianwen-2 mission to Kamoa-Lea, which is the first Earth mini-moon satellite. So these are all the firsts, if you will, for rendezvous missions. And here, what we see is for a rendezvous mission, we can actually look at the body over a long period of time. So we get the shape, the spin state, we get a full global model of these particular bodies represented here. So if these were all the bodies we flew by, these yellow ones are the ones where we actually had a rendezvous and we stopped and looked closer at them. The next level will be a sample return, which is not only did we rendezvous and stop, but we grabbed sample and brought it back home to Earth. So a rendezvous plus a sample return for Earth for detailed characterization. And of course, this requires a re-entry capsule technology. Past examples have become more and more limited. The first here were the Hayabusa mission to Itokawa, the first S-type sampled back and returned in 2010. And then the Hayabusa 2 mission to Ryugu was the first C-type sample. And again, this was closely followed by NASA's OSIRIS-REx mission in 2023. Upcoming missions here are the MMX mission to Phobos to bring back the first samples from that Martian moon. And then again, the planned Chinese Tianwen-2 mission, which will bring back samples from Earth mini-moon satellites. There are
Sorry, Dr. Daniel, you're muted. Dr. Daniel, can you hear me? Hello?
Yes, we can hear you.
Yeah, I think you're muted.
Oh,
If you can unmute, please.
I don't control the.
Yeah, we didn't control anything, but
Yeah,
can you hear right now?
Now we can, yes.
Yeah, okay. Sorry, I don't have any control with the volume. But just looking at the technologies used for OSIRIS-REx and Hayabusa 2 are very, very different from each other. Shows you that it's an area where you can bring creative engineering practices to potentially come up with something even better. So all the flyby and rendezvous, some of them have actually resulted in sample return as well. That's the green ones. When we're actually at these bodies, we're also able to carry out geophysical investigations and surface interactions with these bodies. These include direct measurements of the mechanical and physical properties of these small bodies, subsurface and interior, and also include gravity field measurements. Some past examples are gravity field measurements of Eros and Bennu, the Hayabusa at Itokawa, which tried to deliver a rover which actually failed, but it did interact with the surface. The Philae lander at the Comet 67P, it delivered a lander to the surface, even though it failed to secure itself to the surface. And finally, the great success of Hayabusa 2 at Ryugu, where it delivered several different rovers, Minerva rovers, the mascot rover supplied by the European Union, and carried out a cratering experiment, as was described by Dr. Tsuda. There are upcoming surface interaction and subsurface measurement experiments that are planned. The Hera mission to the binary asteroid Didymos, MMX mission to Phobos, and the OSIRIS-APEX and Ramses missions to Apophis. And these science interaction approaches are very interesting. Here we have a movie from one of the Minerva rovers on the surface of the asteroid Bennu. Here's a high resolution of the surface taken by the mascot spacecraft delivered to the Ryugu surface. Here we see the surface of the Comet 67P along with the lost rover that got wedged between some rocks, and the very exciting SCI experiment at Ryugu. So if you really think about who's done a complete surface interaction experiment, it really is only Hayabusa 2, I believe, to date. But I think this is a clear area for future exploration. So to end up with a couple of slides, the first question is, what is left to do? There have been all of these great missions. What are the additional scientific benefits that we can find? Well, for each one of these approaches, flybys, rendezvous, or sample return, there are still many different approaches that we can take. For flybys, there are specific types of asteroids that remain to be observed, such as triple asteroids, active asteroids, fast spinning asteroids, etc. We can do potentially a survey of multiple asteroids and asteroid types. We can characterize small hazardous asteroids and carry out impact experiments on them. For rendezvous missions, it's possible to do detailed characterizations of asteroids of interest, especially multi-body systems. We can measure the mechanical properties of surface, subsurface, and interiors. We can determine the formation process of these rubble pile asteroids and their evolution in order to better understand the early solar system. And importantly, we can develop technologies for future resource extraction and utilization. And finally, for sample return, we can continue to document the meteorite-asteroid connection, understand cosmochemistry of the early solar system, and develop technologies for processing and transport of materials from asteroids to other locations in the solar system. Possible motivations for each one of these missions, I think, can be found. For flyby missions, I think a clear focus could be planetary defense, focused on characterizing the small near-Earth asteroid population that we have very little data on as of now. These missions are very short, fast, and they give us a fast return on investment. They also tend to be popular with the public. For rendezvous missions, I believe we can dig into the surface and subsurface operations on these asteroids, measuring the mechanics of microgravity materials, the physical and mechanical evolution of these small solar system bodies. There have been initial experiments, but the design and further development of these scientific interaction experiments is, I think, an open question that's ripe for further development and exploration. It's also necessary in order to develop in situ resource utilization. Again, a topic of great interest. Finally, for sample returns, I think the focus on volatile rich asteroids and more exotic asteroid types would also have a large scientific payday. Even though these tend to be more complex missions, they also are of great interest to the scientific community. In terms of cost and time to scientific return, however, this ordering always holds, which is flybys are cheaper, can be done faster than rendezvous missions, which in turn are cheaper and can be done faster than sample return missions. So depending on where you are in this sequence, the type of asteroid mission you may want to focus on may differ. I just have a list of the necessary instrumentation that we could use for these, but I think this gets a little bit too detailed, so I'm not going to talk about that. But to end up, I'll actually share a new idea that was just funded by NASA, and it's called the gravity poppers concept. And it is designed to actually track the particles that you'll see in a second, and it will allow us to measure the internal mass distribution of an asteroid or a comet to very high precision. But I'll just end on this because it's sort of an exciting movie to see. And if there's time, I'm happy to take some questions, either online or from the audience.
Thank you for the presentation. So I think we have some time to get the question, but as you noticed that we will get the question from the online first. So I think we have a question from the chat room. So yeah, from the Wait Materi, thank you for the presentation. My question is for Dr. Barr.
I think that's a previous one that they had there.
Yes, what's the data
Yeah, these are from the earlier.
earlier presentation?
Yes, we covered that question. Thank you so much, Dr. Daniel, for the presentation. I would like to invite anyone who has any question to Dr. Daniel to raise your hand. I think Dr. Mariam, you can go ahead.
So thank you, Dr. Daniel, for your informative session. And if you allow me, I'm having a question. From your opinion, to what extent are the international partnership are truly collaborative in asteroid mission design? Are they driven more by competition between space agency? What do you think? Thank you so much.
Yeah, the question, I believe, is what drives international cooperations in these asteroid missions. And I think in general, they have been oftentimes driven by the space agency level. I know that we've had a lot of interaction between NASA and the European Space Agency and NASA and JAXA, focusing on asteroid exploration missions. There are also models where national space agencies can actually interact with maybe not the governmental agencies in the US, but even with some of the universities and research labs. One example that I'm aware of is the United Arab Emirates are working very closely with the University of Colorado in the Laboratory for Atmospheric and Space Physics on this future EMA mission that will have 6 flybys and 1 rendezvous. So I think that there are many different approaches that can be taken in this area.
Thank you, Dr. Daniel.
Yes, so we have time to get only one question from the online, then we will move on to the mic to the room the listeners in here. Do you have any question from the MS Teams? We can take only one question for the time. Anyone? Yeah, okay, then I will transfer my room in here.
So thank you so much. Moving to our next item in the agenda, I'd like to invite Dr. Jenson Lee, Senior Researchers in KAIST Space Institute, to take us through history and future of small satellite development in the Republic of Korea. Floor is yours, Doctor.
Hi, do you guys hear me okay?
Yes.
Okay, let me share my slide 1 second.
Show you on this. Okay, perfect.
Okay, so I'll get started. Good afternoon or good morning to everyone in Saudi. My name is Jin-Sung Lee, and I am working at the Satellite Technology Research Center, abbreviated as SATREC, as a senior researcher focusing on space mission design and orbital mechanics. And it's truly an honor for me to introduce the Satellite Technology Research Center on behalf of all the members that's working together. So I would like to give a brief history of SATREC, then continue to currently ongoing projects and at SATREC, and end by introducing a newly initiated institute as part of KAIST called the KAIST Space Institute. The Satellite Technology Research Center was established in 1989 by our founding director, Professor Choi Sun-dal. Professor Choi Sun-dal was an engineer at Jet Propulsion Laboratory, but he came back to his home country, South Korea, to start the development of space sector. And number of founding members of SATREC was sent to the University of Surrey at the United Kingdom to learn the basics of space systems, and the legacy of the SATREC began from there. So in total, there were 11 space missions developed in SATREC starting in 1992, with the first satellite ever built and flown also developed as SATREC. Something that SATREC can be proud of is that all of the missions were successful unless there were a problem with the launch vehicle. And most of the spacecraft developed in SATREC were either Earth observation satellite or mission focusing on space science, such as astrophysics and space weather research. I joined SATREC at 2019, so I was lucky enough to join when most of the technology were already, matured. Thanks to all the seniors working so hard for the past 30 years. We have all of the core facilities to develop, test, verify, validate, and also operate the spacecraft inside the SATREC campus. Yes, and we do have a big antenna on top of our very small building. And we also have a, one of the things that you won't be able to see around that much is the attitude control simulator, where you are actually able to mount the engineering model or qualification model for spacecraft and cancel out the magnetic field of the Earth to simulate how the spacecraft would sense the magnetic field and also the sun from ground. So now let me introduce you some of the previous and ongoing projects at SATREC. So I don't think I have enough time to introduce all 11 missions. So I've chosen 3 most recent mission and 1 research planning project that I am very personal to. So the first mission that I want to introduce is the next SAT-2 mission. There were a number of payloads worth mentioning in this mission, but the highlight of this mission was the SAR payload, which stands for Synthetic Aperture Radar System. And it's worth quite a bit of praise, I think, because this entire synthetic aperture radar system was developed in-house. The synthetic aperture radar sends light and measures the time the light takes to travel back to the satellite to map the depth of the ground, measuring from the spacecraft. And because it is using light, the spacecraft is able to map the ground even through clouds or during the night. For this spacecraft, we are in a special orbit called dawn-dusk orbit, which provides continuous sunlight to the spacecraft for generating power. And some of the picture taken from this mission or this satellite can be seen on the bottom. And as you can see, they're all black and white. And the reason for that is because we are only measuring the depth, not the color. Another mission that we are currently developing together with our brother company SatTrak-I is the microsatellite constellation system. The constellation that we are building is comprised of 11 satellites in 2 very special orbits called the Sun Synchronous Orbit. Our first satellite from the first 11 were launched last year with the Rocket Lab's Electron launcher from New Zealand. The 10 of the remaining satellites will be launched with the South Korea's launch vehicle developed by KARI called KSLV-2 next year and a year after. One second. How does that? Okay. So the next mission is the active debris removal satellite mission. Hi, are you guys able to see the monitor?
Not yet. I think it's.
Okay.
Can you stop sharing and reshare, please?
Yeah. Hi, are you guys able to see the monitor again?
Yes.
Okay. Yeah, so the next mission that I wanted to talk to you about is the active debris removal satellite mission. I'm sure that you have heard before the space objects in the low Earth orbit is becoming a serious problem. And it really is a true problem as more spacecraft are required to use their fuel left on board not to elongate their mission so we can maximize the scientific data return, but to dodge the spacecraft or some kind of a debris that is, doing nothing in space. So in order to prevent from these events from happening and to keep the space environment clean, there has to be some type of international collaboration to bring them down artificially, and the risky objects that are currently orbiting the Earth without doing anything good. And this mission is doing just that. We will be docking with a spacecraft in orbit, bring the orbit's periapsis down, which is the closest point about the Earth's surface. And our spacecraft will be jettisoning the spacecraft that we have docked with, and we will raise the orbit to capture another debris, while the debris with the lower periapsis will re-enter the atmosphere and burn up in the atmosphere. Another project that is not yet building, but in a research development and planning phase is an asteroid exploration mission. Together with Professor Shears, who gave presentation before me, who is an expert in asteroid explorations, we are mapping the asteroid exploration roadmap for the newly established administration in South Korea called KASA. Though it is not guaranteed that we'll be getting the grant to carry out this mission, we are trying our best to do so. So now let's talk about the future. So the KAIST Space Institute's goal is to leverage the SatTrak's existing satellite program to establish a research framework that takes the current capabilities to a next level that meets greater complexities. And some of the research fields that the KAIST Space Institute will pursue is, they're listed there, biology-based space health, space cybersecurity, materials and components for extreme space environments, mission design, and deep space navigation. And I myself will put my best efforts in the mission design and deep space navigation section to seek and develop new missions and successfully operate the spacecraft to understand our universe better. This page somewhat summarizes our recent works that we have done that we're proud of, and some of the things that we are currently working on. For example, the return mission or the active debris removal mission. And we have two additional pictures here. One is Van Allen belt probe and far beyond Earth with an asteroid picture showing that we are targeting an asteroid for our next target mission. But most importantly, we want to share our vision, which is by using the 30-year-long developed technologies in SETREC, we will pioneer the next 30 years of South Korea's space exploration. Yeah. So I would like to end by showing you our director's favorite picture, sending KAIST the mascot robot to Mars. And when he says it with a very straight face. So this is not a joke, but yes. Okay, that's all I have for today. If you have any question, please ask. Thank you.
Thank you, Dr. Lee, for the very insightful presentation. I'd like to invite everyone to ask questions to Dr. Lee. Thank you. Go ahead, Dr. Mariam.
Thank you, Dr. Jin Song, for your presentation. It really well delivered session. So I'm asking about, as I'm leading the academic affairs or the university affairs. So I would like to ask you: are there any project where do you work with the student to build the satellite or designing a core mission and operate their satellite? Or their contribution only on outreach and doing maybe joining you for just being in the sideline?
Yeah, so I have two questions for that. One is that we do have an education system in SETREC right now called the New Space Leader Program, where we are accepting about 10 students for about 2 years, and then they get to learn with the people who is actually building the spacecraft and learning, based upon their interest. And another one that I wanted to highlight is that recently we have opened a KAIST Space Institute, and our director was successful in getting new fundings for building a bigger building where we will be able to have number of new testing facilities and operation rooms where we are not, always operating, but we can actually practice operating the spacecraft in deep space. And yeah, there could be a lot more room for us to develop, not only, actually building the spacecraft and getting it to operate, but bringing the students in so that they can get prepared for their later careers.
So based on what you said, those students that you accept in your facility, it's only a Korean, or it's like open for the international student?
So as far as I understand, I think it's open to international students. The KAIST itself is a university. It's not really a security hardened research center. So anybody around the world will be able to join the KAIST Space Institute and be educated in operating the spacecraft and building the spacecraft.
Thank you so much.
Thank you. If there's any other question, I would be happy to answer.
Feel free to write your questions in the chat if you feel like it, or you can raise your hand.
Yes, please feel free to email me for any questions if you have. I'll be happy to answer your questions.
Okay, thank you so much, Dr. Lee, for the insightful session. And I would like to thank everyone for their time and for explaining different concepts of space. I'll leave it now to Ms. May Dosari, Acting Sector Head of Partnership in Saudi Space Agency, before we close this session. Floor is yours, May.
Thank you, Mushal. As we conclude this joint workshop between the Saudi Space Agency and the Korea Aerospace Research Institute and KAIST, we extend our sincere thanks to all those who took part, the distinguished speakers, enthusiastic students, and everyone who took part in organizing this workshop. Your presence and contributions made this event a true success. The valuable knowledge exchanged and the inspiring dialogue shared today mark an important step toward a deeper cooperation in space exploration. This workshop builds on the momentum of the Memorandum of Understanding signed between our two nations in the peaceful uses of outer space back in March, which laid the foundation for a strategic collaboration across various space domains. Today's gathering is a tangible example of that MOU in action, translating shared ambition into practical engagement, mutual learning, and capacity building. We reflect with pride the insights shared today by our experts from both sides and the active participation of the next generation of space explorers. This gathering not only deepens our bilateral cooperation in space exploration, but also inspires future scientists and engineers to pursue ambitious goals beyond our planet. Together, we reaffirm our shared commitment to advancing space science, empowering youth, and exploring vast opportunities that lie ahead in space. We truly hope that our students today have enjoyed the technical presentations and hope to see some of you working in the space sector in the near future. Thank you.
Thank you, May. Thank you again. Thank you, everyone, for your time. And we'd like to thank also our speakers. You provided such wonderful insights to students from both sides. We can conclude this session and hope to see you next time, inshallah. Thank you so much. Have a good day.